morning everyone. Today we are going to see the deflection of beam by moment area method for a cantilever beam. Myself S.K. Karthikeyan, Associate Professor, Department of Mechanical Engineering, Kombunadu College of Engineering and Technology. Now we are going to see the problem. So the problem is a cantilever type of arrangement. So there are 2 point load given in the problem. You see a cantilever of length 2 meter carries a point load of 20 kN at the free end and another load of 20 kN at its center. If E equal to 10 power 5 Newton per millimeter square and I equal to 10 power 8 millimeter power 4 for the cantilever, then determine by means of moment area method the slope and deflection of the cantilever at the free end. So they are asking slope and deflection at the free end. So first you construct the diagram for the given data. So now you have seen this diagram. This is the solution for that given statement. So you have 2 point loads. One is 20 at the center and another one is 20 at the free end. The total distance of the beam is 2 meter. So you have to give equal spacing 1 meter and 1 meter. Now what we are going to do is we are going to find the bending moment. So for this arrangement you start from the right side. So there is bending moment at C from right. So you simply mention it as BMC, suffix C. Okay. So BMC equal to 0. That is because of the rule when you going to calculate the bending moment at the free end mean it's going to be 0. Always 0 at the free end. Next, bending moment at the B, that is at center. So you are finding from right side. So at B the formula is force into distance, vertical force into horizontal distance. Vertical force is 20 into 1, that is 1 meter. So 20 kilonewton meter. So that going to be converted into Newton millimeter, that is 20 into 10 power 6 Newton millimeter. Then you are going to find bending moment at A. So that is also finding from right side. So you have 2 loads now. One is at the free end, another one is at the center. So now we are going to start from the free end. So that is 20 into 2 up to A, that is 2 meter. So 20 into 2 plus the center load is 20 into the distance up to A is 1. So 20 into 1. So you are going to have 40 plus 20, that is 60 kilonewton meter. So as usual you convert the thing into Newton millimeter, that is 20 into 10 power 6 Newton millimeter. Next we are going to construct the bending moment diagram. You see the free end is 0, at the center 20 into 10 power 6 Newton millimeter and at the fixed end is 60 into 10 power 6 Newton millimeter. So when you construct the diagram means you are going to have 3 portions. One is rectangle, another 2's are right angle triangle. So you simply give the naming as 1, 2, 3. The 1 is right angle triangle and the 2 is it's a perfect rectangle. The third one is a right angle triangle. So there are 3 portions. Now I am going to show the formulas. The formulas are totally you have the 2 formulas. One is slope at the free end, that is area of the bending moment diagram divided by EI. Another one is deflection at the free end, that is YB equal to AX bar divided by EI. So YB means deflection at the free end. So that is simply noted as Y. So these 2 are the formulas. The third one is slope and deflection at the center always 0. So we are only calculating at the free end only. Now coming to the finding of total area. So this is the method to find the total area of the diagram. You split all the thing as 3 portions. That is total diagram into 3 portions. 2 right angle triangle, another one is rectangle. You give the naming as 1, 2, 3. The first one is right angle triangle. For that we are going to find the area. A1 is the term we are using for finding the area of the first portion. So the formula is half BH. So half into CD into BC. So half into 20 into 10 power 6 into 1000. So finally you got 10 power 9 Newton millimeter squared. Then second portion is a rectangular. The formula is B length into breadth, BH, that is A2 equal to BH, CD into AC. So that is 20 into 10 power 6 into 1000. So finally you got 20 into 10 power 9 Newton millimeter square. Then third one is right angle triangle, A3, half BH is the formula, half into ED into EF. So finally you have half into 1000 into 40 into 10 power 6. So finally it's going to be 20 into 10 power 9 Newton millimeter squared. Add all the three areas, finally you got 50 into 10 power 9 Newton millimeter squared. So this is the A, we are going to use it in the formula, that is slope at the free end. So slope at the free end is theta B equal to area of the bending moment diagram divided by EA. So area of the bending moment diagram is the A, so 50 into 10 power 9 divided by EI, that is given in the problem, that is 10 power 5 into 10 power 8. So finally you got 0.005 radians. So this is the slope at the free end. Now we are going to find the next one, that is deflection at the free end. The formula is AX bar by EI. So we have to find AX bar. So the expansion of AX bar is A1 X1 bar, A2 X2 bar, A3 X3 bar. So A1, A2, A3 are the known things, that is as 10 power 9 20 into 10 power 9 20 into 10 power 9, that you have known already. So the X1 bar, that is the thing we are calculating from the free end. So when you go for finding the X1 bar from the free end, means it's going to be 2 by 3 into L. So A1 into X1 bar, that is 10 power 9 into 2 by 3 into 1000. 1000 is the length. Plus the second one is A2. So for reaching A2 you have to came across 1000 meter. So that is mentioned as 1000 plus the rectangular half distance, that is 1000 by 2. So that is the X bar value. So A2 is 20 into 10 power 9 into 1000 plus 1000 by 2 plus A3 20 into 10 power 9 plus the 3 is in the second portion, after 1000 only it going to be started. So 1000 plus 2 by 3 into length, that is length of that portion is breadth is 1000. So finally you got AX bar as 70 into 10 power 12 Newton millimeter square. Now you substitute this AX bar value in the Y formula, that is AX bar by EI, 70 into 10 power 12 divided by 10 power 5 into 10 power 8. So you are going to have 7 mm. So this is the answer, that is deflection at the free end is 7 mm. Thank you all.